Welcome to the SAR channel, where sound and audio are demystified. Before an analog sound can be saved, sent, or edited on a computer, it must first be turned into a digital form through three main steps: sampling, quantizing, and conversion. The hardware that performs this includes parts like a Dither Generator, anti-aliasing filter, sample and hold circuit, analog to digital converter, and channel code modulator. The most common and basic example of this process is the linear Pulse-Code Modulation (PCM) system, which served as the foundation for later digital methods. The bandwidth of a recording or transmission system shows how wide a frequency range it can handle without losing too much signal strength. For example, an audio signal sampled at 48 kHz with 16-bit resolution has a data rate of 48,000 samples multiplied by 16 bits equals 768 kilobits per second. When extra data for synchronization, error correction, and modulation is added, the total bit rate can reach around 1 megabit per second for one monochannel. The goal of digital recording is to capture sound as accurately as possible while keeping the bit rate efficient and manageable. Modulation is a way of encoding information so it can be sent or stored. The most common type is Pulse-Code Modulation, PCM, where an incoming analog signal is sampled, quantized, and encoded into digital form. In PCM, the strength, amplitude of each sound sample is turned into a binary number, allowing computers to represent the sound with digital pulses. At playback, these binary codes are used to recreate the original analog waveform. Because PCM stores exact amplitude values, the signal can be reconstructed without loss. In a linear PCM-L-PCM system, the analog sound is first filtered, then sampled over time, and its amplitude is quantized by an analog-to-digital converter AD. During playback, the digital data is decoded, corrected for errors, and passed through a digital-to-analog converter DA and low-pass filter to rebuild the analog sound wave. Essentially, an audio digitization system is a two-step process. It converts analog audio into digital data for storage or transmission and then converts it back to analog for playback. Though it sounds simple, the system's design quality is crucial, as it directly affects how accurate and natural the reproduced sound will be. Dither is a small amount of noise added to an audio signal to reduce unwanted digital artifacts caused by quantization. It makes the signal fluctuate slightly between nearby quantization levels, which helps eliminate quantization errors and allows the system to represent sounds that are quieter than a single quantization step. While Dither introduces a bit of noise, it removes harsh distortion, and the ear generally finds soft noise less unpleasant than distortion. When Dither is added before the analog to digital conversion, it helps the converter preserve very quiet details in the sound. The digital system must have a wide enough dynamic range to capture everything, including the faintest sounds within the noise floor, without adding quantization distortion. The word length of the quantizer, bit depth, must be long enough, and its least significant bit, LSB, must be properly dithered. Whenever the bit depth is reduced, for example, converting a 20-bit recording to 16-bit, dithering and noise shaping must be used to maintain sound quality and avoid distortion. An incoming audio signal can contain very high frequencies, some of which may be above the Nyquist frequency, half the sampling rate. To follow the Nyquist theorem and prevent unwanted noise, digital audio systems must remove these high frequencies before sampling. This is done using an input low-pass filter, also called an anti-aliasing filter, which blocks frequencies above the Nyquist limit while leaving the audible range unaffected. An ideal filter would perfectly pass all wanted frequencies and completely block unwanted ones, without changing the signal's phase. In practice, this is difficult to achieve, so engineers use digital filtering and oversampling in modern AD converters to approximate ideal performance. In early systems that relied only on analog filters, the signal had to be sharply limited to frequencies below half the sampling rate. However, such brick wall filters caused problems like uneven frequency response and phase distortion. To fix this, engineers sometimes use smoother filters, but those reduce some audible frequencies too. To balance this, they increase the sampling rate, often up to 3 times higher, to allow enough filtering and still avoid aliasing, though this also increased the amount of data. For instance, when recording at 48 kHz, filters are designed to pass sound cleanly from 0 to 22 kHz, leaving a 2 kHz safety band to block unwanted frequencies near the Nyquist point. Good filters must minimize overshoot, ringing, and phase distortion. Filters with steep cutoffs often cause ringing near the cutoff frequency and delay certain frequencies, known as group delay. Engineers can correct this by adding a compensating delay circuit, resulting in a smooth, natural sound. Because analog brick wall filters degraded audio quality, modern AD converters now combine a gentle analog filter with oversampling and precise digital filtering. No matter the method, every digital audio system must use an input filter to remove frequencies above the Nyquist limit and prevent distortion. If you've enjoyed this video so far, please hit the subscribe button for more. Thank you. Let's continue. A sample and hold (SH) circuit has 2 main jobs. It takes regular samples of an analog signal at specific time intervals and holds each sampled value steady while it is being converted into a digital number by the AD converter. Without this hold function, the analog signal might change during conversion, leading to incorrect digital results. In short, the sample and hold circuit captures a snapshot of the analog voltage and freezes it for accurate digitization. An audio signal can be fully described by its time and amplitude, and the sample and hold circuit captures both. It samples the signal at evenly spaced intervals, using a clock or oscillator that sends timing pulses at the desired sampling rate. These pulses tell the circuit when to take each sample. In its simplest form, a sample and hold circuit is made up of a capacitor and a switch. The circuit follows, or tracks, the incoming analog signal until the sampling command closes the switch, isolating the capacitor and storing the signal's voltage. The capacitor then holds that voltage steady while the AD converter measures it. The circuit must acquire the correct value very quickly. If it takes too long, the converter might record an average instead of the exact instant value. To prevent this, the sample and hold circuit must be precisely designed and driven by an accurate timing clock. Jitter, or small variations in sampling time, can introduce noise and distortion, especially for strong, high-frequency sounds. Therefore, the sample and hold circuit's clock must be extremely stable, typically controlled by a quartz crystal oscillator, to ensure timing accuracy and keep noise below the quantization noise floor. The acquisition time is the delay between when the sample command starts and when the sample is actually taken. A longer delay can lead to inaccurate values depending on how quickly the signal is changing. Once the sample is taken, the sample and hold circuit must hold that voltage steady during conversion. Any small voltage loss, called droop, can occur due to leakage in the capacitor. Good design and component quality can limit droop to less than half of one quantization step. In summary, the main errors in a sample and hold circuit are acquisition time errors and voltage droop, and minimizing both is key to achieving accurate AD conversion. The analog to digital converter. AD converter is the core component in the encoding stage of a digital audio system. Its partner, the digital to analog DA converter, handles playback, but any errors made by the AD converter stay with the audio throughout all processing and storage. Therefore, the accuracy and quality of the AD converter have a major effect on the final sound. The AD converter's job is to read each sampled analog signal, match it to the nearest quantization level, and output the binary code that represents that value. It must do this for every sample quickly and precisely. All converters have a small, unavoidable quantization error of about 1/2 least significant bit, so dithering is used to reduce distortion. The conversion time, the time it takes to output each digital word, must be shorter than the sampling interval. If the converter cannot keep up, timing errors can appear, affecting accuracy between samples. These dynamic errors become worse at higher sampling rates. A high-quality converter keeps total error below 1/2 lsb, minimizing offset, gain, and noise errors. However, temperature changes can cause drift, leading to inaccuracies. Many converters are calibrated at the factory, and multi-turn potentiometers can be used to fine-tune gain and offset stability over time and temperature. Converter quality is often judged by harmonic distortion testing. When a pure sine wave is input, the output should contain only that tone. Any extra frequencies in the output, harmonic multiples of the original, show distortion. Because random noise is also present, this is measured as THD plus N, total harmonic distortion plus noise. Unlike analog systems, where THD plus N decreases as signal level drops, in digital systems it usually increases at low levels. For this reason, THD plus N is measured at both high and low signal strengths. Another key measurement is dynamic range, which is the difference between the loudest possible signal and the noise floor. AD converters are also sensitive to jitter, which is variation in the clock's timing. Random jitter increases noise, while periodic jitter adds distortion by creating sidebands around the main tone. A good converter keeps jitter low through a stable internal clock or clock recovery circuits that filter out timing errors from external sources. However, a low jitter clock alone does not guarantee better performance. The converter's overall design matters most. Even tiny timing variations can degrade audio quality if the circuit or power supply is unstable. To minimize jitter, accurate quartz crystal clocks are used to control all AD and sample and hold timing. Although many converters claim 24-bit resolution, true 24-bit performance is almost impossible with current technology. In theory, 24-bit audio would reach a noise floor near -145 decibels fs, equal to about 0.1 microvolt RMS, similar to the thermal noise of a small resistor. In real systems, background and electronic noise make this level unachievable. Internal processing may use longer word lengths, but practical AD and DA converters cannot yet capture or reproduce signals with true 24-bit precision. The successive approximation register SARAD converter is a traditional and reliable method used for accurate audio digitization. It works using a feedback loop made up of a digital to analog DA converter, a comparator, and a control circuit. The converter compares the incoming analog voltage with a test voltage created from its current digital estimate. It then keeps adjusting this digital value until the two voltages match within the desired precision. In simple terms, the SAR converter follows a step-by-step process. It checks each bit, starting from the most significant one, and changes it as needed until the digital output perfectly represents the analog input signal. Traditional analog low-pass filters have drawbacks such as added noise, distortion, time delay group delay, and uneven frequency response passband ripple. Because of these issues, it is hard to achieve more than about 18-bit resolution when using them with standard AD converters. To overcome these limits, most modern systems have replaced brick wall analog filters and SAR converters with oversampling AD converters that include digital filters. Oversampling converters work by sampling the signal at a much higher rate, often 64 or 128 times 44.1 kHz, and using a sigma-delta modulator to process the signal. This high sampling rate allows even short word lengths, one or a few bits, to achieve very fine resolution. The sigma-delta design also performs noise shaping, which pushes most of the quantization noise outside the audible range. Compared to SAR converters, oversampling AD converters offer much higher accuracy. They spread quantization noise far beyond the audio frequency range, leaving less noise within the audible band. Their built-in digital filters not only prevent unwanted noise generation, but also remove frequencies above the audio range, producing a cleaner and more accurate digital signal. If you've learned anything new so far, please like the video. It really helps the channel grow. Thank you. Once an analog signal is converted into digital form, binary numbers, Several steps are needed before it can be stored or transmitted. The system typically performs multiplexing, interleaving, error correction, and channel coding to prepare the data properly. Some digital audio recordings use a process called pre-emphasis to reduce noise. Before recording or transmission, high frequencies are slightly boosted. During playback, de-emphasis reduces those frequencies again, which helps lower overall noise levels. In analog systems, any storage or transmission errors directly cause audible problems. In digital systems, however, error detection and correction are used to fix most defects and maintain quality. Interleaving helps protect against large data losses by spreading information across the bit stream so that a single damaged area affects only small parts of the audio once it's deinterleaved during playback. Because digital audio is usually transmitted as a serial bit stream, a multiplexer is used to convert the parallel data output from the AD converter into a single continuous data stream. The multiplexed data is divided into frames, each identified by a synchronization code so that the system can keep track of where each frame begins. Additional information can be included in these frames, such as addressing, timing, or identification codes. These codes may store details like the sampling rate, whether pre-emphasis is used, the table of contents, track timing, and copyright data, ensuring proper playback and data organization. Channel coding happens before the signal is stored or sent. Digital audio samples are made of ones and zeros, but they are not usually transmitted in raw binary form. Instead, they are converted into a modulated channel code that represents the audio and other related data. During playback, this modulated code is interpreted to recover the original binary data and recreate the sound. Directly storing binary data on a medium is not efficient. Even though digital recording is about saving zeros and ones, the actual recorded signal often looks different. What matters most are the transitions, the exact points when the signal changes from one state to another. The channel code defines how the data is modulated, stored, transmitted, and then demodulated back into a readable signal. In this process, information bits are converted into channel bits. A good channel code must be self-clocking so that the receiver can stay synchronized with the transmitter. This means the decoding clock at the receiver must match the timing and phase of the transmitted signal. Frames in the bit stream are identified using a synchronization word. Without it, it would be impossible to distinguish between channel bits. Codes that can maintain timing automatically and support fast data transfer are called self-clocking codes. The purpose of channel modulation is to merge the data and clock signals into one waveform that carries both timing and information. Different modulation codes are designed depending on the storage medium, but only a few are suitable for digital audio recording, whether magnetic or optical. Simple codes protect each data word on its own, while group codes treat a set of bits as a code word and add redundancy across the group, improving error detection and correction. Thank you for watching till the end. To better understand each video, make sure to watch the previous ones. Some may serve as prerequisites for the next. If you have any questions or opinions, feel free to leave a comment. Until next time, subscribe and stay curious.